We have a problem right here. Model a car suspension system where M is the mass of the body, K is the suspension spring stiffness, B is the shock absorber damping, RT is your road profile impede, and your YT is your car body displacement output. So let's start with Newton's second law. What do we know about Newton's second law? We know that Newton's second law is the summation of all forces acting on the body is equal to the mass times acceleration. So let's analyze the forces acting on the body. Analysis. So first we have your spring force. That's your Fk. Right here, your spring force. And that is equals to K times the displacement. That's equals to K times Y of t minus R of t. That's your car body displacement and your road profile impede. Then next we have damper force. That's your Fb. That's equals to your B multiplied by the differential of the displacement. That's Y of t minus R of t over dt. Then you also have your inertial force, Fm. Fm equals to Na. That's equals to your M multiplied by t square Yt over dt. So now that we know the forces acting, we can plug them into our Newton's second law. Now that we know the forces acting, we can plug them into our Newton's second law. The summation of all the forces will not be minus Fk minus Fp is equals to Ma. So from this, our Fk is K Y of t minus R of t minus, let's not forget the negative, minus P dt dy of t minus R of t over dt equals to your M multiplied by t square y, sorry, this is square of t over dt square. So from here, to make it easier to write, we can just use prime. To make it easier to write, we can just minus K Y C minus R C minus B open brackets Y prime C minus R prime C equals to your M multiplied by your Y prime of T. So rearranging the equation, you have your M Y prime minus K Y T plus K R T minus B Y prime plus B R prime. So your M Y prime C. Rearranging the equation, you have your M Y prime C. Rearranging the equation, you have M Y prime plus B Y prime plus B Y prime plus K Y is equals to your BR prime plus KR of T. So note that this came here, became plus, this one came here. Like this, we have gotten our differential equation using Newton's second law. Second question is to find the transfer function. So to find the transfer function, to make it easier to find the transfer function, we are going to convert this to Laplace. plus the y prime prime of t becomes s squared. This your y prime of t becomes sy. Your y becomes ys. Your r prime becomes s rs. Rt becomes r of s. Then so now we're writing it in Laplace. We have m s squared ys plus b s plus k ys equals to your b s rs plus k rs. So we factor out our ys and our rs. That will be ys equals mx squared plus bs plus k equals to factor out your rs. That will be rs. That will be bs plus k. And we know that our transfer function g of s will be equals to your outputs over your inputs. And your output is y of s over r of s. So that will give us ms squared plus b s plus k, ms squared plus b s plus k under your bs. So this is your transfer function of your suspension system. Suspension system. Our next question is to explain the physical role of each parameter. So, m is the mass of the car body. Is the mass of the car body. So this provides inertial force like resistance to change in acceleration. The larger the mass, the slower the system natural response will be. So can relate this to our m is the mass which provides inertia, and it is the resistance to change in acceleration. You also have your k, which is your suspension spring stiffness. So we have all seen it in our cars, like some of us, that spring beside your wheel. Like if you look deep inside your vehicle wheels. So your spring is it provides the restoring force proportional to the spring compression or elongation. If you have seen a spring before, you see that when you stretch it, it returns back to its original. Provides the restoring force proportional to the spring compression or elongation. If you have seen a spring before, you see that when you stretch it, it returns back to its original position proportional to like how you bent it. So it supports the static weight of the car body and determines the natural frequency of the suspension. So the higher your suspension, like the higher the value of your P is a shock absorber. So we have a shock absorber too from our vehicles. This is what absorbs the impact of the vehicle. Like if you enter like a pothole, so this, or if you have all these off-road vehicles, see that they have big shock absorbers, so you won't feel the impact of any disturbance. So it provides dissipative force proportional to the speed of the suspension movement. So its primary role is to dampen the oscillation caused by the spring and quickly bring the mass back to equilibrium. So it prevents excessive bouncing and improves ride comfort. Your R of t is your roll profile. Its primary role is to dampen the oscillation caused by the spring and quickly bring the mass back to equilibrium. So it prevents excessive bouncing and improves ride comfort. Your R of t is your roll profile. Yeah, you have even written it. It's a roll profile input. This is the external disturbance or input function. So it is the position or displacement of the road surface, like where your wheel is, and where your wheel is. Then your y of t is your car body displacement. So this is the system response or output function. So it's the vertical displacement of the car body, and the variable is used to determine how comfortable the ride is. So that's all for the physical role of your car suspension system. We have a problem right here. It said model a robotic arm joint where J is the moment of inertia, BR rotational damping, KR rotational stiffness. Okay. C of T is your motor torque input, your theta of T is your joint angle output. So now we add summation of our torque. Sum of our torque is equal to root 2, your moment of inertia multiplied by alpha. Now let's do the torque analysis. You have your input torque, our T of T. You have your damping torque. Plus TBR plus TBR, and that's equals to the BR multiplied by d theta of T divided to T. Also write it as BR of theta prime of T. And we have your spring torque, theta prime of T. And we have your spring torque, CK. CK. That's your K multiplied by your your joint angle output. So, and also note that your alpha is equals to your theta, the second order differential of your angle output. So putting your torques inside the formula, you have your T, your input torque, minus your damper torque, minus your spring torque, equals to your G theta prime prime of T. Putting it inside, substituting your values, that's your T of T minus BR theta prime of T minus K theta of T equals to your G theta prime prime of T. Now we have gotten our differential. Let's rearrange it as G theta prime prime of T. Now we have gotten our differential. Let's rearrange it as G theta prime prime of T plus BR theta prime plus BR theta prime of T plus K theta of T equals to your T. So we are done with the first question. We have derived the differential equation. Now let's find the transfer function. To find the transfer function, we have to convert it to our S domain. So the theta prime prime of T will become S squared theta S, and your theta prime of T will become S theta S. So theta of T will become theta S, and your T of T will become T of S. So substituting this inside the differential equation, converting it, you have your G S squared theta S plus BR S theta S, then plus K theta S equals to T of S. So factor out your theta S. You have theta S open bracket K theta S equals to T of S. So factor out your theta S. You have theta S open bracket JS squared plus BR S plus K equals to T of S. Yeah. And now your transfer function G of S equals to your theta of S over T of S. That will be equals to 1 over JS squared plus BR S plus K So this right here is your transfer function. Now they ask us to find, to compare this with problem 1 and discuss the similarity. So our first problem, we solved the gas suspension system. Now they ask us to find, to compare this with problem 1 and discuss the similarity. So our first problem, we solved the gas suspension system that's to do with linear motion. Now we're solving robotic arm joints. That's to do with angular motion. So I'm just going to paste like a picture. So we can see that the rotational robotic arm model is an exact analogy to the translational gas suspension system, as if the gas suspension were modeled with a fixed input force instead of a road profile based excitation. So they're basically the same thing. The only difference is just the linear motion and angular motion. Here you can see the mass. The mass is moment of inertia. So resistance acceleration, the damping coefficient for gas suspension is rotational damping for robotic arm. It opposes the velocity and reduces oscillation. Your spring stiffness is for gas suspension is torsional stiffness for robotic arm joints. So it's a restoring force or torque pulling system back to equilibrium. Your road inputs is also the same as your motor torque inputs. So for gas suspension system, this was not fixed. So that's why we have your YT minus RT when we're calculating. But for our robotic arm joint, it was fixed. So this is the external input forcing the system. And your YT body displacement is your joint angle for robotic arm joints. So this is the system output displacement. And when we calculated from our answer, this is what we got as your second order differential equation. So that is the same thing, except from this values that are changing. Then for our transfer function, so they both produce second order transfer function. So that's all for this problem.